Okay, now we saw in the last slide that when we superimposed the Gaussian or normal curve onto our binomial distribution, where we have fattened our bars to represent area, that it wasn't a perfect fit. And the line would cut through, each one of the bars on the corner. And so you would just naturally kind of assume, well, wait a minute, that's not a perfect fit. So then how can I expect that the approximation is going to be close? And you'd be right. It won't be. There'll be error. And so if you look here on the slide down here, this here is our exact binomial calculation using the formula that we gave you. And when you do so, in this case, for trials, as we know, it's a fair coin, right? So 0.5 is the probability. But in this case, we're interested in 3 heads or more. So we're on the right tail. So then we would add the far right 2 bars, and we get an answer of 0.3125. Great, makes sense. Now, if we wanted to approximate using our normal curve, then we would take the area under the curve that represents 3 or more heads. So you literally just draw a line down, on the 3, and take that area, and you'll see that the approximation is poor. It's like, well, wait a minute, that's off by quite a bit. However, if you are to shift, where you cut down the area by half, so you're going in between 2 and 3, it improves the approximation tremendously. And now you're like, oh, that's actually pretty good. And this is called Yates' correction factor for continuity. And you're still going to say, so I'm sure many of you are thinking, yeah, but wait a minute, buddy, 0.3085 is not 0.3125. And once again, you're correct. And the reason for this is just because, it's easier for us to use a very small data set as an example where you can actually manually write out all 16 results that are possible so that you can visualize it and do the calculations by hand easily. But with such a small n, it is extremely challenging for the normal distribution to approximate, and we're gonna cover this a little later, and actually later on in this lecture. And so, if you truly were working with this small a data set in this problem, you would forcibly have to use the exact calculation of the binomial using the equation. This is just an example for you guys to understand that you can approximate the binomial distribution with the normal distribution. However, it works well as your sample size increases, or your n, your trials, increases. Okay, time for a statistical interlude. So on your right is Frank Yates, who actually just passed away recently in the 90s, the mid-90s. So Frank Yates is responsible for introducing the continuity correction factor that we just talked about. So the ability to approximate the binomial distribution using the normal curve, the area under the normal curve. Now you're probably thinking, well, who cares? I mean, I have, the exact binomial calculation that I can just use anytime and I get an even better answer. I don't need to approximate it. Well, you'll see that later on in the course, we're going to introduce you to the statistical model, and that's what you're interested in, actually. You're actually interested in building a model that's going to be able to predict an outcome. And by putting in multiple predictors to predict a single outcome, you're going to come to realize as well that dealing with that kind of a model is challenging. It's tricky. And what we need are tools that will allow us to do exactly that, is to analyze and then interpret the results from a statistical model in such a way that it's actually possible, not only in terms of computational, power, but also in being able to put all those variables together in a single model and making sense of it. And this is where these type of simple rules and simple findings or approximations or verifications that we're showing you come into play. It allows us to later work with more complicated models and actually get interpretable results. So more about that later. On your left is Jacob Bernoulli, and he's a mathematician, and this is just out of interest that he's the one who coined the term a Bernoulli trial from the flip of a coin, and he's also responsible for a few other things like the law of large numbers, as well as E, so ln, the natural ln, and he had a particularly interesting hairdo. No, I'm sorry. Okay, moving on to the next slide. Okay, math alert. Avert your eyes if you're math adverse. No, I'm kidding. So in this one, we're just simply introducing you to the concept of the Gaussian probability density function. And we've used it. So essentially, it's the approximation of the binomial distribution using the normal curve. In this case, you're going to say, okay, well, how do I draw the normal curve? How do I get that normal curve? Well, this is what it is. This is a math function. As you know, math functions are basically relationships. Here's that nice equal sign, which I'm pointing without my laser pointing around. I'm sorry. Here we go, that equal sign. And essentially what it's showing you is that you need, of course, your little p, which is the proportion of 6 subjects in a random sample. This is what you're interested in. This is the whole concept of expectation. And pi, you know what pi is. E, we just talked about it, which is that math constant that Bernoulli was kind enough to elucidate for us, which is also the base of the natural log. Here's your probability. So in this case, P would be, let's say, the probability of being sick, and Q is the probability of not being sick, or if you wish, it would be heads versus tails, whatever you'd like. Big P, or capital P, is the proportion of 6 subjects in a population sample, so within the population. And once you add all of this all these wonderful numbers into your Gaussian probability density function, you can then get your expectation. So basically, what's the probability of, and you let me know. Now, in our example, for instance, all the possible proportions that we were working with, you'll recognize them. 0 heads was 0.0625, 1 heads was 0.25, 2 heads was 0.375, 3 heads was 0.25, and all heads was 0.0625. Then you're going to say, well, what the heck is the 0 and the 1? Well, it's because it's a curve, and if you remember correctly, on the very, very far left and the very far right bars of your histogram, that curve went past that bar, the outside of that bar, and then down to the x-axis, and that's what this represents. The 0 and the 1 means that those lines will go and get as close as possible to the x-axis. So this is something we're going to talk about fairly frequently, and that is the normal curve, or the Gaussian curve. And this density function is the one that gives you that curve and the area under it. And in this case, it is applied to a binomial problem, if you wish, where you have a probability of an event. Okay, let's dig into an example. So using a single cohort design, a researcher tests the curative ability of a new drug. Now, she follows 10 patients and records their sex, age, and weight, the typical outcome predictors. And in 8 of the 10 patients, she observes that the new drug is successful. In 2 of the patients, the drug has no effect. So in this case, we have a binary outcome: yes, successful, no, not successful. So we begin by assuming that the probability of a cure is the same for each patient and is actually 0.5. So a equal chance of successful or not successful. This assumption is called the null hypothesis or the chance hypothesis, and we're going to talk about this a lot in the coming slides. So therefore, the probability of getting an 8-2 split that this researcher observed can be obtained using the binomial probability distribution, and you could calculate it by hand using the equation that we used in the previous slides. And in this case, P, as we've stated, is equal to 0.5. Okay, let's have a look at this binomial distribution where n equals 10, which are your 10 pairs. The probability, or the null hypothesis, or the chance hypothesis of this probability is 0.5. So it's a flip of a coin. Okay, so what we've done here is we've listed, you see here on the left is the exact binomial equation was used to calculate the probability of, once again here, if you were to pick, let's say A, so A having 0 cures, A having 1 cure, 2 cures, blah, 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 all the way to 8 cures, 9 cures, 10 cures. So in this case, when we said an 8-2 split for A, we're going to be saying we need to add up the probability of getting 8 or more in this split is going to be summing these 3. Now, obviously, you can just flip it the other way around because we always work in two tails. You can flip it the other way around and you have B that's going to be 8 or more. And so that's why we've highlighted in red here that you can have B 8 or more is going to be essentially, A 2 or less. So you're going to have these. And if you add these up, then you're going to get the probability for either of these tails. Okay, and so this is where we're showing here is if you do your cumulative probability, this is then once you do cumulative, you see it goes from 0 to 1 or from 1 to 0, of course, depending on the direction. And you're going to have your two tails. Okay, so the cumulative probability is going to be 0.05469 on each tail. And this is the graphical representation of the previous slide where we just got the numbers, but you can see on the left and the right are the 8 or more or 2 or less, the two tails, for the probabilities of getting, in this case we said number of heads, but it could be, the treatment, successful treatment. And you have your cumulative probabilities, which we'll see next. Now, though you guys are now experts in calculating exact binomial probabilities, maybe we can start asking our software to do it. And so here's the introduction, our first slide on SAS software. So this is the software that we prefer to teach with. That's actually the software that I actually use as well for my statistics. And it is available to you as the SAS University Edition, which is free, downloadable. You put it on your PC or your Mac and away you go. We're going to cover more and more of the programming and the abilities of SAS throughout the course. So I'm not going to do it all here in this one slide. But here, just to show you quickly, I'm just putting a little quick title. Freak is a procedure that we are going to use here, and it's our first program. Now, data final just simply means, I'm creating a data set that the procedures will be using. I'm calling it final. I'm inputting a variable called cure with a $sign, which means it's going to be a character and not a number. N, which is going to represent my count. And then don't worry about the other symbols. We'll go over that after. Data lines. Now I'm entering the data. So I have, for cure no, I have 2 counts. For cure yes, I have 8 counts. Run, which means away we go. Let's put the data set together. We then put together our procedure, the freak procedure or the frequency, proc freak, data, just read the data set I just created, final. The weight just means the 2 and the 8 are the counts for each of my 2 options, which are yes or no. And then I'm asking to do a binomial probability distribution calculation, and I would like it to do not only, which we will see with the approximation from a normal distribution, but please also give me the exact binomial, and I have to ask for it. The output here that I show at the bottom of the screen, and I'm going to get my laser pointer, here we go. This is the output that would come. So this part here that I'm circling here with my laser pointer is the code that you would have to run, and this is part of the output that you would get in HTML format, which arrives on your screen. And basically this little table here is just saying, you know, for each cure, so for the variable cure, no cure frequency is 2, then it gives you your 20%, your cumulative frequency is 2 because it was the first line. And then you have cure yes, you have a frequency of 8, your percent is 80, and your cumulative frequency at this point is 10 because you have 2 plus 8 is 10. There we go, 100%. Okay, so the next 2 slides is just a nice written summary of what I just went through in the previous slide, setting you up to run ProcFreak for the first time on your computer. And just to remind you, you can copy and paste the information in the slide directly into your programming window in your software, your SAS software, and press run, and it will give you the same results that I'm showing you on my slides. So this slide and the next slide, please just read through them to help you get a little acquainted with how SAS programming works. Okay, so here's the second slide, and now we're going to move on